Welcome to the second part of my research presentation. In this video, we will focus on developing a physics-informed deep learning paradigm for traffic state estimation. In the previous video, we have covered the introduction to this research problem and also the relevant mathematical background regarding PIDL and TSE. So if you're looking for all those preliminary informations about this research, please refer to the part 1 of this video series. In this section, or in this video, I'm going to talk about mainly 4 subsections here. The first part is what is physics-informed deep learning and how that applies to TSE. And then we will see the formulation of PIDL using the LWR traffic flow model. And we also see the formulation of it using the cell transmission model. And finally, we will see a series of case studies for application and validation. So what is physics-informed deep learning? It is a type of deep learning that encodes the inherent physical laws as a priori knowledge. So in equation 26, we see the cost term or the cost function of PIDL consists 2 cost terms. Let's just say that. And the first one is JDL, which is the estimation cost, and that computes the accuracy of my final state estimation. And the second cost term is JPHY, which is the physics cost. And that measures the compliance of the physical law or governing physical equations here. And these slides further formulates these 2 cost terms here, JDL and JPHY. And what I want to point out is NU here symbolizes the number of training samples, or in the context of state estimation, that is the number of your state observations that can be used for training. And NF here is the number of collocation points. Collocation points are where the physics cost is computed to verify the compliance with physics. So this slide gives an overview of the optimization of PIDL. So as we see, this figure has mainly 2 major components. On the left, we see a fully connected regular deep learning neural network, which takes in the input of variables such as x, y, z, and t, and gives the output, estimation output of u. And on the right, we actually see this physical part in play that adopts automatic differentiation to compute various derivative terms given the governing equation, which is listed as a function f here. And so both components play a role in this optimization process. So the deep learning neural network on the left produces this JDL cost, which measures how different the estimation of u is compared to the ground truth. And on the right, these parts will compute the cost JPHY, which gives how your estimation is not really satisfying the governing equations of physics. And in the end, those two cost terms are combined to give us the final or total cost function of this PIDL neural network. So how this optimization works in the context of traffic state estimation, I'll show you in the next slide. So here is a flow chart of physics-informed deep learning for traffic state estimation. So on the left, we first actually see this training data set, which is observation. So here, this figure shows by using these 3 horizontal lines actually depicts the traffic data that's being captured by, for instance, loop detectors, which are stationary, buried under the road surface, collecting data. And that's the training data that we are going to use. And usually that data is too limited and not being able to really recover or reconstruct the entire picture. So what it does here is we use that training data, we feed into a deep learning neural network, we get a tentative estimation results, and then we compute these two major cost terms. The first one is the estimation cost, and the second is the physics cost, where we compute at collocation points and to get the partial derivative terms of their state with respect to location x, with respect to time t, and get the final cost. And then we combine or fit into this cost into this optimization process until we get, in the end, a satisfactory results as an estimation output. Now we will move on to the second subsection where we formulate this PIDL approach using LWR model. So here we are going to show the formulation with LWR with two different types of fundamental diagrams. The first one will be the Green-Shields fundamental diagram, and the second one will be the inverse lambda fundamental diagram. So here, equation 28 shows actually in the traffic state estimation setting what the JDL and what JPHY will look like. And here we already encode the LWR equation into the JPHY cost term. And so I want to point out these two data sets here. The first is set O, where is the observed data set, and that represents all our traffic observations. And the second is set C, where it's a set of collocation points that where the physics costs are computed. Recall or like why we are using the fundamental diagrams here is because they relate traffic state variables by their modeling functions, such as we have Green-Shields fundamental diagram, we have other fundamental diagrams such as Dagonza, such as inverse lambda. So here, these equation 29, equation 30 are both LWR equations paired with Green-Shields fundamental diagram. It's just in equation 29, you see all the partial derivative terms are about the velocity term v, and in equation 30, you see the partial derivative terms are about the traffic density rho here. And subsequently, pairing the LWR with Green-Shields fundamental diagram, we will get the JDL and JPHY formulation in equation 31, which is when we can reconstruct a density field rho, or in equation 32, and now the state variable of interest is velocity here. I also want to mention that a second order diffusive term can be added to make this PDE a parabolic PDE, and that will secure a strong solution. And the point here is this diffusion term ensures the solution of this LWR PDE is continuous and differentiable and avoids breakdown and discontinuity. Without this diffusion term, or as we previously seen in the mathematical background, that if we set the epsilon value to 0 and cancel out this diffusion term, and this PDE will become a hyperbolic PDE and doesn't have a strong solution. And if you have like any doubts, just as a general reminder, if you have any doubts regarding those equations, or if you want to see any details, you can just pause the video and take a closer look and see which each cost terms or partial derivative terms means in those equations. So next, we actually will formulate this PIDL with LWR model and another type of fundamental diagram, which is inverse lambda fundamental diagram. Recall in the inverse lambda fundamental diagram, there is a capacity drop between before there's a capacity drop after your density reaching the critical density. So here, the JPHY take two forms. One is before the capacity drop, and the other is after the capacity drop. And NC1, NC2 are the number of collocation points in the free flow region and the congestion region, respectively. So coming next, we will formulate the PIDL approach using the cell transmission model here. And recall, what is cell transmission model? Cell transmission model will formulate or consider the traffic flow, or to model these traffic conditions by separating the road infrastructure into continuous homogeneous cells in between. And this figure shows a discretization of space-time domain in CTM. And here, let N1 and N2 be the number of bins after discretizing these density fields in space and time domain. And here, equation 35 will give the formulation of the physics cost term JPHY here. And in the next slide, we also see the general assumption of CTM that there is a uniform density rho in each cell, and there's a uniform flow between adjacent cells at each time interval. So we can further formulate the cost function or the cost terms JDL and JPHY in equation 36 here. And now this slide focuses on how would we compute the flow between adjacent cells, and to answer that question, the good enough numerical solution is deployed, which is a finite difference scheme. Recall in the mathematical background section that we understand if the characteristic speed on the left is greater than the speed on the right, then that calls for a shockwave solution, or shockwave will develop. And if the characteristic speed on the left is smaller, that we will land at a rarefaction solution. So this shock speed is given in 37, and how we can determine the flow between adjacent cells here. Q is using equation 38. In equation 38, this rho, we can say like rho star, is denoted as the flow dictating density. And how we determine the value of this flow dictating density is using the Goodenough numerical solution, which is shown in equation 39 here. So now finally, we covered all the mathematical formulations of PIDL for TSC. And finally, we can see a various of case studies for this type of application and a validation of how PIDL works in terms of traffic state estimation. First, let me introduce the selection of learning instances. So in the sub-figure A here, that shows a typical learning scenarios for mathematically solving a partial differential equations, such as Berger's equation. You have all the boundary conditions, you have all the initial conditions. But usually that's not very realistic in the traffic data collection scenarios. Because what that means would be you have a stationary detector, stationary sensors deployed and collecting data all the time, and there is like no data loss, and is collecting continuous data, which is usually not possible. We usually get maybe the sensor data is, we get density values maybe like every 10 seconds, every 30 seconds. And also the initial conditions would means you are actually maybe using a drone or like traffic camera and collecting the traffic state values at all possible locations, which is also incredibly difficult. A more realistic scenario would be depicted in the subfigure B, where you have some boundaries data and some initial conditions. Or like even more realistic, you would have scenarios or data as learning instances in subfigure C or D. And C, you see that, oh, that's black marks just marks the traffic observations from the stationary sensors. And in the D, that data can be collected from, let's say, connected autonomous vehicles or probe vehicles such as GPS data, where you have like scarce observations of this entire field. So in the first case study, let's create a synthetic data set by using the Lax-Hopf methods. And in this case study, we are investigating two scenarios. The first is the Eulerian sensing scenarios, where from what we just seen in the subfigure C, using stationary sensing devices. And in the second scenario, we will use randomly selected data and deploy PIDL to estimate the traffic state here. We established this evaluation metric, which is relative L2 error, shown in this equation 40 here. Let's see the results. So in the first sensing scenario, we used 100 samples, represent merely 0.4% of this entire field, which is also marked on the right by those black marks. We see those marks are not continuous, indicating or like replicating the realistic scenarios. Sometimes the data may be lost. Sometimes the sensors are not functioning or like online all the time. But using these mere data, 0.4%, what we find is actually PIDL can still capture the traffic pattern and reconstruct really well. And under the same scenario, a similarly configured DL, a regular deep learning neural network with the exact same learning architecture, just without the physical knowledge, will just not gain any insightful knowledge of the traffic conditions and to fail the reconstruction task. And let's move on to the random sampling scenario, where now we actually see the randomly selected data are going to well represent the traffic state in this entire image, in this entire domain. And now what we observe is both learning approaches will achieve considerably good results. And in this case, PIDL will have the huge advantage of saving computational time. And that is the main advantage of PIDL in this scenario, given the training data is already well represent this entire domain or the entire image. Now we move on to the next case study, where we use Lagrangian sensing like data collected by probe vehicles and see how, in this case, PIDL will perform. We designed this experiment data set regarding velocity with a more complex upstream downflow conditions. And on the left, this subfigure A shows a 1% CAV fleet scenario. So in this data set, there are 403 vehicles passing through on this road. So 1% represents 4 vehicle trajectories, as we see those black dots are collected along the vehicle trajectories. We also will notice considerable gaps in this image, or like along those black dots, and that means we consider the scenario where this data is collected by the roadside units, and each roadside units will have their realistic data coverage areas. So if the vehicle is traveling between the covered areas, that data will not be obtained by the RSUs. So which means like the data is lost. On the right, we establish another scenario, excuse me, where we have 10% of the fleet enabled as CAV data and will be able to transmit the data. And here we present the sensitivity analysis of various penetration rates. And the conclusion here is PIDL will consistently outperform DL with respect to the computation time and the accuracy, which is depicted by the relative L2 error here. And similarly, we also conducted the sensitivity analysis for the various data noise levels. And we will observe the similar results that PIDL will outperform the DL approach as well. And finally, with the last case study, here we deploy the realistic NGSIM data set, and this velocity data is obtained during afternoon rush hours on I-80 in California, and we do observe the shock waves propagating backwards in this figure or in this data set. And first, in order to adopt the LWR model from this release data set, we need to estimate the critical parameters of this traffic flow model, which are the free flow speed and jam density or maximum density. And they are given here in this slide. And this slide presents the reconstruction results are given 10% or 14% of the observations. So on the left column, where we see on the top is the PIDL reconstruction or PIDL for KIC using 10% of observations. And on the lower left, that's the DL model with 10% observations. On the top right or upper right, that's PIDL with 14% of observations. And the in the lower right, that's the DL with 14% of observations. So we see like consistently, actually PIDL will be able to capture that shock waves or the relationship of the traffic flow here, and being able to accurately reconstruct the traffic state. And DL, what we observe is just overfitting here and not really producing a meaningful meaningful understanding of the traffic conditions here. And here's the summary that we compare the relative L2 error here. This case study also demonstrated the superior performance of PIDL in terms of reconstruction accuracy, given limited training data, comparing to the deep learning approach. So finally, let's recap this video and let's recap of all the contents in this video and what we have learned. So in the discussion part, the first point I want to make is actually the supply of physical law, which is the main difference between the PIDL approach and DL approach, is an information gain to the neural network. And in that sense, the physics cost term can be viewed as a regularization agent in this optimization process and prevents overfitting, which is shown in the case study with NGSIM dataset that DL is just overfitting the traffic observations. And this advantage, this information gain, brings improvement in both estimation accuracy and curtailing or shortening convergence time. The second point in this discussion is the incorporation of the physics cost term, JPHY, introduces collocation points in the training process. And what that means is actually the compliance of the physics can be measured at much more locations in timestamps, like you may have only, in the first case study, you only have 0.4% of the training data, but the JPHY cost term can be measured anywhere at any location at any time, and that gives much more opportunity to gain the information on JPHY and providing aid to the optimization process. And so that compensates to the really limited numbers of training instances of traffic for the purpose of TSC. So that concludes the second part of this video. And in the next and final video of my research presentation, we are going to see the analysis of PIDL for TSC and how we can improve that. And that will also conclude this research presentation. So I'll see you there.